you said just grade it out of 5 or something.
Yeah, well,
I thought it was out of 1.
this, I mean, graded out is something that when you turn it into a floating point number, it's between 0 and 1. And,
Okay.
actually, the way I'm entering all the grids into Sage, and I'm just entering them as they're, as they're written. So they'll get simplified to be floating point numbers at some point. So you could actually put transcendental numbers into it.
Or use E points.
So essential discriminant divisors. Computation of a P maximal order and general factorization of primes.
It is.
So those are the 3 main topics. Essential discriminant divisors, I'll do those very quickly because I already gave you the main example last time. I just didn't give a formal definition. So definition, so let K be a number field. And essential discriminant divisor is a prime P such that P divides the index in OK of any monogenic order. So this is for all A in O sub A. In other words, no matter what element you choose in the order to generate some monogenic order, the index is still divisible by P. So that's an essential, that's called an essential discriminant divisor. This P will have a property that its square automatically divides the discriminant of OK, because after all this, well, wait, back. Sorry, this is a prime P that automatically divides the discriminant of any order generated by a single element. It actually doesn't have to divide the discriminant of OK. So that's a definition, and I showed you an example last time that involved f equals x cubed plus x squared minus 2x plus 8. So that particular polynomial has the property that if you look at the corresponding number field, then 2 is an essential discriminant divisor. Let's see some facts about these. There's only finitely many essential discriminant divisors for a given field. If you fix a field, there's only finitely many. And that's just because, I mean, each of these are an integer. So just considering any A, so that ZA has finite index in OK, you see that the set of essential discriminant divisors is finite. And then, I mean, the actual essential discriminant divisors are the GCD, really, or the product of the primes dividing the GCD of all of these indices. So, so 2 can be one, and I think actually any number can be the discriminant divisor of some field. And I think that I don't actually know the relation between the possible essential discriminant divisors and the degree of a field. I just have no idea. So I'll just make that a question. In case you're very curious, you might try to solve it. Question, is there an, say a function, what is this? I'll make it as plain of language as possible. Is there a bound on the essential discriminant divisors in terms of the degree of the field? field. In other words, if you have a cubic field, is it obvious that maybe only 2 could be an essential discriminant divisor? I don't know, but there's a question to throw. I think for a quadratic field, you don't have any essential discriminant divisors. Well, I know that. So, for example, this, when the degree is 1 or 2, there are no essential discriminant divisors.
Can you say anything about the number of essential discriminant divisors? Like, you know, you said that it had to be finite, but if it's a cubic extension, there are at most 2, or
If you answered this question, that would say something about the number, but
could be.
it could be that the answer to this question is no, and then there's some statement about the number. I suspect that it's going to be that, I mean, it's not going to be so much that there's a bound on the number, but just on the actual primes that can appear. That's what I suspect. But you could certainly ask also for how many there could possibly be for a given degree. I have no idea. I've never really thought about this question. In fact, it just occurred to me right now. So if anybody wants to think about this, could make a good project. All right. And just recall, in this one example, what happened is we had OK, and we had 2 times OK. This factored as a product of 3 distinct primes in this cubic field. And that meant that there was no way that 2 would divide anything like this. Because if this were co-prime to 2, you could just factor the min poly of the A, and that would give you a factorization of the ideal 2. But you would get a factorization which doesn't look like this in the theorem or the proposition that I stated before. Okay? All right, so let's move on. The second thing I'm going to sketch for you is how to compute a p-maximal order in general, which I mentioned before that I may or may not do that. And now I'm going to do it modulo proving a certain theorem of Post and Zassenhaus. The proof isn't that hard, but I don't think I have time to do it. And you can look up the proof in Cohen's book in section 6.1.1. Yeah, could you turn the camera up? Thanks. So now on to part 2, which is computation of maximal order. So the picture you have in your mind now is that you have an O some order, which might be Z adjoining A, but it could be something else. It's contained inside of an O sub K. And what you'd like to do, the problem, is that you want to find an O prime that contains O and is contained in OK, of which P divides this index. Because if you could iteratively do that, then you would eventually find O sub K. At least you'd find something that's for which this index is co-prime to P. And then you could do this for all primes P, whose square divides the discriminant, and you would arrive at O sub K. And you'd have an algorithm for computing O sub K. So that would be nice to be able to do. First, the naive algorithm for enlarging O to O prime, which I mentioned already, is you simply consider 1 over P times O, which is a subset of the number field K, may or may not be contained in O sub K. But you just list the finitely many elements of 1 over P O mod O. So view this O as a lattice. It's a free Z module of rank equal to the degree of the number field. 1 over P times O is another free Z module. It's just you take all the vectors and divide their coordinates by P. So that gives you 1 over P O. This quotient is abstractly isomorphic to a finite abelian group that's just product of n, where n is the degree of the field. K, Q, the product of n copies of Z mod PZ. So this is a finite set. You just enumerate through all of them. For each one, you choose some lifting to an element of 1 over PO and check whether or not it's integral. And that will give you an order like this. That will give you an O prime. But that's really slow because the complexity of doing that is P to the n steps. You have to compute P to the n minimal polynomials, which is ridiculous. So you don't want to do that. So fortunately, there's a theorem due to Post and Zassenhaus, which once I state it, you'll see that if you believe the theorem, then there's a better algorithm than what I just described that involves some linear algebra and other things. And it involves all kinds of interesting tricks. But basically, the thing to keep in mind is the following theorem. So the context, the notation, everything's like over here. We have an order O, we have a prime number P, and we have, abstractly, we haven't computed it, but we have this ring of integers OK. So here's what we do. Let I sub p be the radical of the ideal generated by p, which means the set of x in O such that some power of x is in PO for some n greater than or equal to 1. So you consider this order O, multiply it by p, you get the ideal generated by p, and then take all elements that have the property that some power of that element is in p times O. So this is the radical of p times O from commutative algebra. So let's let IP be that, and it's clearly a subset of O by definition. So now here's the thing you do. You let O prime be the order associated to this ideal I sub p, the radical. The order is by definition the set of elements of K that preserve IP. Okay? So that's what you let O prime be. And now here's the conclusion. Then O prime is an order, and either O prime equals O, in which case O is already P maximal. That's the content, that's the main difficult part to prove in this statement. In which case O prime is P maximal, meaning that the index of O in OK is co-prime to P. Or, if it's not, they're not equal, or O prime properly contains O, and the index is a power of P. Some power of P to the, let's say. P to the J. Okay? So that's the theorem of Poston-Zassenhaus, which takes maybe a half page to prove if you know enough commutative algebra. So it's not that bad to prove, but it does require some work. I'll prove a little bit of it. Namely, I'll prove that the index of O in O prime is a power of P. In other words, this construction gives you an order that fits into a picture like this, so that the index here is a power of P, and the O prime is contained in OK. I'll just prove this part, that this is a power of P. The hard part, though, again, is checking that if O prime equals O, then you're done. It's already P maximal. And of course, you also have to turn this theorem into an algorithm, which means how do you compute I sub P efficiently using a computer, A, and B, once you've computed I sub B, how do you compute O prime, again, efficiently using a computer? Those are both the things that one can do. So I'll just sketch a little bit of the proof of the Poston-Zassenhaus theorem. So for the main proof, see Cohen's book. I'll just explain a little bit of it. So I will prove that the index of O and O prime is a power of P. And then after doing that, I'll explain how to use the theorem to actually do calculations. I'll tell you how to turn the theorem into an algorithm. Okay, so now, so let's prove this. It's actually not too hard if you just look at the definitions. We have to take an element of O prime, and I'll show you that any element of O prime is actually in 1 over P times O. So really what we're doing here in this construction is we're somehow just using linear algebra picking out exactly the right elements of 1 over P O 1 O. Okay? That's the beauty of this. So suppose X is in O prime. That means that X multiplies IP into IP. Well, in particular, X multiplies every element of IP. into IP. And here's a particular element of IP, the number p. It's an IP, right? Because, I mean, p to the power 1 is in p times n. So, x times p is in IP. Just because that's just, I mean, just follows from the definition of O prime. All the elements of the number field that multiply every single element of IP into IP. I'm just using p as one of those elements. So x times p is an IP. And IP is by definition an ideal inside of O. So x times p is an element of an ideal that's a subset of O. Therefore, x is in 1 over p times O. So I just proved for you that this O prime is contained in 1 over p times O, which proves the statement that that index has to be a power of p. Because the quotient O prime mod O embeds inside of this finite abelian group. Okay, any questions? Yes, Robert Miller.
So you know that OK is free abelian?
Yes.
And that's what I forgot. Okay.
Yes, that's something from, I guess, the second week, when it's a finitely generated, when we proved that OK is an Theorem, we proved that by showing that OK is a finitely generated free abelian group. So that makes it easy to think about the structure of this. And in fact, its rank, the rank of OK, so abstractly OK is just isomorphic to z to the n. Product of n copies of z, n is the degree. So that's what I'm using here. So just think about kind of everything I'm doing, just think about lattices. We've chosen some basis for K as a vector space over Q in such a way that maybe all the elements of OK, that's z to the n inside of that Q to the n, that vector space isomorphic to Q to the n. So you can think of this is C inside Q to the n, which for an appropriate choice of basis is isomorphic to K as a Q vector space. So forgetting about the ring structure when I write this isomorphism here. Okay, so other questions? So this construction, this definition of O prime, which is very constructible in that there's an algorithm to efficiently compute it, picks out a certain order that you get from elements of 1 over PO. And I mean, to really prove this, though, you need to do a little more work. You need to see, for example, that every element of O prime is an algebraic integer. How do you see that, actually? How can you tell that this x has to be an algebraic integer? Remember the trick we used like 4 times before. So what does this x preserve?
There's some integral ideal, right?
Yeah, it preserves an ideal. An ideal is a finitely generated Z module. That means that if you write down the matrix for x in terms of a basis for IP having finite index in OK just as a abelian group, we see that this x is given by a matrix with integer coefficients, integer entries. Therefore, its characteristic polynomial is monic with integer coefficients, so this x is an algebraic integer. So that's how you see easily that this is contained in OK. So that actually proves that the picture looks like this. And now the only thing I haven't proved for you in this post-Zassenhaus theorem is that if O and O prime happen to be equal, then you're already P maximal. That's the only thing I haven't proved. And I'm not proving it just because it's actually pretty tricky to write down proof. It takes a while. Okay? So now let me make a few remarks about how to compute O prime. In other words, what's an algorithm that'll just spit out O prime very efficiently for you? So maybe you can move the camera back over here. computing the post-Zassenhaus O prime. And the ideas that go into this, I think, are pretty general tricks that are useful in a lot of contexts, so it's good to know about them. So let's say you want to compute first I sub p. So I sub p is by definition this radical, the radical of p times O. So it's an ideal. If you add together two elements, well, I mean, actually it takes some work to prove that the radical of an ideal is an ideal, but you can prove it. If you add together two elements, you get something that's in there again, and if you multiply two, you get something that's in there again. Okay? So this is something that I'll assume you know from a course in algebra, that this is an ideal. But then let's see how we could compute it. So this ideal, the first observation is it contains p times O. And that's going to make things much, much more computable. The reason is just, I mean, actually, I guess I already mentioned why, but certainly if you have an element of p times O, its nth power is also multiple of p. Pretty straightforward. Now that means that, so you have your order O, and inside of it you have this ideal p times O, and now you're really desperately interested in computing actually IP, which is sitting here. Okay? But you know from algebra that if you have a commutative ring and an ideal here, then you can look at the quotient, O mod PO, and the ideals of O that contain PO are in one-to-one correspondence with the ideals of O mod PO. So, in order to compute IP, what you do is you instead compute the radical of the zero ideal over here. And this is a finite set. This is finite, so that's going to be easy. Or not easy, but there's a good way to do it. So this is finite set. So instead of computing IP here, we compute IP here. That is the set of x that are nilpotent. So IP maps to an ideal IP bar in here, where that ideal is the set of x in O mod PO. So at some power 0 in here, i.e. x to the m equals 0 for some m. In other words, the set of nilpotent elements in the string. Now here's where it gets kind of cool. There's, you don't have to, you might think you have to just iterate through this entire ring in order to compute the set of nilpotent elements in it, but you don't. This is actually equal. The set of nilpotent elements is equal to the kernel of a single matrix phi, where you view O mod PO as an n-dimensional FP vector space under addition, and this phi is just powering, some powering map. You can choose some, so you can find some integer r so that an element is nilpotent if and only if x to the power of r is equal to 0. So you write down the linear transformation x goes to x to the r, and then you compute the kernel of it. So that's it. And you can pretty easily write down an a priori bound on this r. So I'll just write for some computable r, for some single computable r.
Isn't it just n? I mean, or is that a bound?
Let's see, is it, what is the r? Probably not. Let's see.
You can look at the order of FP as a group.
That's a good, remember, but, so watch out. So this is under multiplication. So you have to think a little more, but let's see what you can do. So, and you also need to choose the r, so it's actually, so you have to note that the powering that you're going to actually use is a linear transformation. This doesn't look linear at first, but it is. So let's see, I think we have to prove one, that we can always make the m be a power of p, and that's probably just p to the n. Okay? So, let's see, I didn't think that through completely at the moment. So, I think that's what happens. So the R is a power of P, probably P to the N. I have to think about that for a minute. It needs to be something like that, otherwise this won't even be a linear transformation. So you won't be able to compute it as a kernel. But that, I mean, that's the key observation, is that the set of nilpotent elements are the kernel of a linear transformation that you can just write down on a basis and use linear algebra to compute, which is really a powerful idea. Because the only other way to compute this, if you didn't have that idea, is you'd have to just iterate through the whole thing. At least the only way I could think of, and that would be completely hopeless. Whereas this is incredibly fast in practice. So let's see, I'll just think for like a minute to see if I can see exactly why this is true, or if somebody else can. Okay.
Well, doesn't
Yes.
x to the p to the n fix fp to the n?
Keep in mind that this is only as an abstract abelian group that it's isomorphic to fp to the n. So it's really, I mean, the multiplication is not the coordinate-wise multiplication.
Right.
O mod PO could be a finite, it could be fq. I mean, it could be a field itself, which has degree p to the n. I mean, degree n over fp, or order p to the n. So this is only under addition that you have something like this. You should really think of O mod PO as an abstract vector space with a multiplication table that's commutative. Okay? So it's isomorphic to some v. V is an fp vector space of dimension n with a multiplication table. And with a multiplication table. Which is commutative. But it of course is this. So let's see.
For the p to the n, if you just look at like kernel, you know,
Mhm.
raise it to the p, raise it to the p squared,
Yep.
those all nest.
That's right.
And if any two are going to be equal, I think you can immediately show that all the ones after that are going to be
Right.
equal. And
That's
so
true.
that
That's a great observation.
actually,
Yeah, that's a great observation. So let's see. Yep, that's true.
are worse.
So all you need to know is that, I guess, that you can, as long as you can take this m to be a perfect p power, then you can use the argument you just stated to get it to be something of this form. So why didn't you take it to
There's
be
a
a
p
perfect
power
power?
bigger than n, so just multiply it by more x's.
Hey, that's a good idea. Yeah, so you can always take m to be a perfect p power. That's a good point. Okay, so okay, so the only thing we need now is an a priori bound on what power of p you might need. So your argument didn't quite give that. What if, what if you needed p to a billion, and a billion is a lot bigger than the degree of the field? That's the one thing.
Dimension argument, right? Because it will go down, like the
Yeah,
successive
I
images
agree.
will.
I agree. Yep, that proves it. Good. I don't know if I've convinced anybody but me, but
Maybe you didn't
and the
prove
two of
it.
you. But that proves it. Yeah, because you're just taking the map x goes to x to the p. That you know on any fp vector. Well, I mean you know that. So x plus y to the p is equal to x to the p plus y to the p. So this is a linear map on this object, and iterating this map definitely will kill any element that's nilpotent, and each time it has some, like you iterate it, you take its kernel, and you take a kernel of it on that kernel and so on, and at some point you have to stabilize. And you can't just keep going. Either you go down or you stabilize. And if you go down, you can only go down n times, because the dimension of the space you start with is n. So this, we just put a p to the n here on the other side. So I'm convinced. Good, great. So, and also the fact that this can be a perfect power, we take to be a perfect p power, as Robert said. You can always make n, you can add 1 to n. I mean, it doesn't have to be, it just put some more x's here. Okay, excellent. So now we've given basically an algorithm to compute IP. Look, all you do, you want to compute IP, so instead you compute IP bar as the kernel of some homomorphism, which you just write down doing FP linear algebra. And then you just take IP bar plus PO, and that gives you IP. This is equal to basically any choice of generators for IP bar plus PO. In other words, if you are explicitly representing everything here as submodules of some, q to the n, which, so your k is equal to q to the n, and you explicitly represent, for the multiplication table, you explicitly represent everything in terms of that, You get IP by taking just a lift, an arbitrary lift of your vectors mod p to here, and then adding to that p times o. And then you'll get some free z module, which, using Hermite normal form or something, you could put in a nice form. So that's how you compute I sub p. So I sub p is efficiently computable. Yes, Robert?
When you're looking at O mod PO,
Mhm.
I'm just curious about how that goes on in computers.
Okay.
Because
Well, I'll tell you exactly how it goes
two
on.
big things, and you mod
No, so here's how you think about it. O, so k is, let's just view it abstractly as q to the n. So then O, it's an order, so it's given by n vectors in q to the n, okay? v1 through vn. And then maybe they have integer coordinates and then maybe they don't. O mod PO, you should think of as, really it's O tensored with FP. You could think of that as just O tensored with FP. So this is tensor over Z with FP. One way to think about this that might avoid confusion is V1 through Vn, you could choose them to be a basis for Q to the n here. You could choose them, in fact, by changing bases so that they're the standard basis for Q to the n. And then this O mod PO is just literally a FP to the n. And the thing you just have to keep in mind is that you have a multiplication structure on K. And that's what you use everywhere here. Like to do this powering, you have to use that multiplication structure. Okay? So when I write O mod PO, all I mean it's, because it's sort of abstract, all I mean is you're taking the explicit Z module basis for O, and then taking P times that Z module basis and taking the quotient. In other words, you take Z, you can think of it as Z linear combinations of your basis for O modulo P. So the coefficients are always modulo P. Does that make sense? So, I can explain it 20 different ways, because it's crystal clear to me. So let me know if it doesn't make sense to you. And I mean, the exact way in which you represent things to carry out the calculation depends entirely on how you actually decide to represent every object. And since I haven't, say, fixed particular representations for everything, it's hard to really say more than I've already said. So, I mean, very often with an algorithm, you have an algorithm in the sense that you have something like this, which you kind of know could be made fast. But then in order to turn it into an actual algorithm that you would run on a computer, you have to choose an incredibly precise representation for every single object involved in the calculation. And there's often a lot of work to translate even a statement like this into a statement that makes sense to a computer. Okay, so that's how you compute IP. And now to compute O prime, once you have IP, it's really easy. O prime is the kernel of the homomorphism from K. Oh, let me think about this for a second. It's a homomorphism from O, actually. Sorry. That doesn't make any sense. Here's it. This is kind of a cool trick. So actually what you do is you consider the homomorphism. So this is 2 computing O prime. So consider the homomorphism psi from O to the endomorphisms of the finite abelian group IP mod P IP. Then O prime is just equal to 1 over P times the kernel of psi of that homomorphism. Okay? So first, does this make sense? This is an additive abelian group. Given an element of O, you can view it as left multiplication on IP, and P times IP is certainly preserved, because P times IP is an ideal, since I is an ideal. So you get a well-defined map, or given an A and O, it's left multiplication by A. It's the endomorphism reduced by left multiplication by A. So that's what psi is. And you view this just as a finitely generated free abelian group. This is also a finite, this endomorphism thing. It's like, you think of it as it's a group of matrices. It's also a finitely generated abelian group. And psi is a homomorphism of finitely generated abelian groups. And questions like, what's the kernel of a homomorphism of finitely generated abelian groups, you can answer using Hermite normal form, which is kind of like Smith normal form. but it's a little bit different. It's the exact analog of reduced row echelon form, but over the integers. So this is a very straightforward computable thing, this kernel of psi. And 1 over p times it, well, that's easy to do. So let me convince you that this is true. So proof. You just check each direction of the inclusion. So first, suppose you have an element of O prime, and I'll show it's in here. So let's say x in O prime, and we want to show that p times x is in the kernel of psi. So if you have an element of well, let's see, is that clear? First, recall that we did prove that O prime is contained in 1 over p O. Therefore, p times x is in O. So we get that. So this at least makes sense. It makes sense to apply p times x. I mean, it makes sense. So p times x is at least in O. So this is clear. P times x is in O. And now we just need to see that it's actually in the kernel of psi. Why is that? It's going to come from the definition of IP. Isn't it? How does that happen? So any element of O prime multiplies IP into IP. So since we're assuming x is in O prime, x actually multiplies IP into IP. So p times x times IP. Let's see what that does. Well, x already puts this into I. This is certainly contained in p times IP, right? Because x times IP is contained in IP. But look, that's exactly the condition to be in the kernel of psi. Cool. Good. So we're done. That's true. Now the other direction, suppose that x is in 1 over p times the kernel of psi. Then p times x is in the kernel of psi. So p times x times IP is contained in PIP, which means that XIP is contained in IP. Which is what we want, right? Let's see. Yeah, because that's just the definition of O prime. Yep, that implies x is O prime. Okay, so now I've proved that you can compute phi prime. To compute phi prime, you just compute the kernel of this linear map of free abelian groups. Or actually, that one's not free, but a finally generated abelian groups. And then we write down 1 over p times it. So now you see, though it's complicated, there is a straightforward, in a sense of complexity, algorithm to compute a p maximal order. Yes?
Why did you mod by PIP when you were looking at the action with O?
Here?
Yeah.
Just because I need to, otherwise I don't get the right answer. I mean, you could certainly, I mean, you could define a map from O to end IP, I guess. But that wouldn't do you any good.
Okay.
This is just exactly the right thing to consider because it works. Or, I mean, do you not agree with the conclusion, or?
No, I'm just kind of struggling with the definition. Like, so
Okay.
if I have something in O and then I multiply that by P,
You're struggling with the definition of this map.
I guess maybe if you could just explain why it's well defined when you take
Sure.
the quotient, that probably.
Okay, sure. So this map is the following. It takes an element A and O, and it gives you left multiplication by A on this. First, IP is an ideal in O, so it's preserved under multiplication by A. In order to prove this is well defined, I have to show you that PIP is also preserved. But that's also true because PIP is an ideal. Okay?
Sure.
So the map is well defined. All right, so I've now given you a complete description modulo, a little bit of an argument of how to compute a p maximal order given a prime p. And this, in fact, leads to really the best algorithm to compute a maximal order in general. You just figure out what primes p you have to use and then p maximize, and then add together all the results. Okay? So that's the promised algorithm for computing a p-maximal order, which is, as you can see, vastly better than just enumerating through these elements. It's more complicated, but it's better. Okay, any questions? So I'm running low on time, so there's really one kind of key algorithm that I need to describe for you that's kind of a generally useful algorithm that you need in order to go from the sort of things I just showed you to factoring prime ideals, primes of primes of z in O. So the last thing I wanted to tell you about was, given O and a prime p of the integers, how do you factor p times O? And what I won't explain is how to find the powers of the factors. I'll just talk about how to find the primes that contain p. So in short, when you compute the radical of p times O, this is the radical of PO, you now know that you can compute it. This is easy to compute in the sense that it doesn't require factoring. It really just requires linear algebra mod p, which is very, very fast, especially because number fields typically have quite small degree. So you compute this p radical. It turns out O mod, well, the p radical is the product of the primes that contains p. Product of the prime divisors of p. So you consider O mod IP. This algebra A, this is a finite separable FP algebra. And there's a structure theorem for these which says they're all products of fields. This is a product of fields. We get this separable just because we've constructed the thing exactly to have no nilpotent elements. So it's a product of fields. And in order to compute general factorizations, you just have to explicitly compute this product decomposition, and then you take the inverse image. If you explicitly have this written as A1 cross A2 and so on, cross AK, where each of these are fields, you could just take everything here and 0 here and take the inverse image, and then that would give you one of the primes. And you can get each of the other primes similarly. So if you can explicitly compute the product representation or some product representation of an abstractly given finite separable FP algebra, which is again a very generally useful thing to want to know how to do, then you can compute all the primes that divide P. The primes are exactly the kernels of the homomorphisms from A to each of the projections here. So this projects to A1, it projects to A2, and so on. Projects to AK. So you just choose any one of these, say A2, you have a homomorphism from A to A2, the kernel of that is one of the primes that lies over P. Okay, so now the only thing I need to tell you in order to enable you to compute general factorizations is how do you compute, given an abstract finite separable FP algebra, a product decomposition like this. And unfortunately, I'm not going to have time to write down much. One way that sometimes works, but doesn't always work, is you take your abstract thing A, compute some random element, find its minimal polynomial, and if the degree of the minimal polynomial equals, is sufficiently large, then you find that it just generates A. So when A can be generated by one thing, you can often just find it at random. Unfortunately, that's not always the case. As that example I had up before, where 2 is an essential discriminant divisor, it had the property that there's no single element that will generate this. You have to watch out because in Cohen's book he says that there always is one in the beginning of his section about doing this, and that's not true in general. But fortunately there is a really nice deterministic algorithm to find a decomposition like this. What you do is you first compute the kernel of the map x goes to x to the p on this finite separable FP algebra. That will give you exactly how many factors you have here, because that gives you the kernel of that map, the map actually is x to the p minus 1. That will tell you exactly which, or x to the p minus x, sorry about that. That will give you exactly the elements here that are in FP. So it'll give you FP cross FP cross FP. So the dimension of this tells you the number of factors. Once you do that, you just take this kernel, which is a product of copies of FP, and you choose some element in there, and you compute its minimal polynomial. You choose some element that isn't diagonal in here. You compute its minimal polynomial, and you can use that to get an idempotent. So you choose an alpha that's in this kernel, but not in FP, and you find its min poly, and then you factor it as m1 times m2, and then in fact m1 of alpha times some other auxiliary polynomial u1 that you find is an idempotent epsilon. That's neither 0 or 1 unless k equals 1. So that's just a very, very quick sketch, but it's a fairly standard, straightforward thing to actually split this basically by choosing an element and then computing its minimal polynomial and then doing some just basic algebra. So you shouldn't understand exactly how to do that because I really haven't explained it. I'm just giving you the barest idea. I did write it up very carefully in the notes, which I just posted today. So I rewrote that part of section or chapter 5. So if you look into section 5.3 at algorithm 5.3.7, I write down in detail exactly how to take an abstractly given finite separable FP algebra and find an idempotent, which as long as k is greater than 1 will allow you to split this, and then you just recursively apply the same algorithm, and you'll end up splitting it completely. So this is a completely doable thing, to split a finite separable FP algebra. And once you've done that, again, you get all the primes back. Okay, so I'm done. If you have any questions, let me know. I will say a little more on either Monday or Wednesday about this, but I strongly encourage you to look at the latest version of chapter 5 in the notes to fill in a few gaps that I wasn't able to explain in class to the time.
What's a separable algebra?
It's a finite, you know what a finite FP algebra is. Separable means each element is separable. It's equivalent to having no nilpotent elements in this case. So in other words, the minimal polynomials are spin-free.
Right.
I know it's something we've
If
been
you weren't,
finding
you'd
out
be
for
able
the
to
last year.
construct a nilpotent element.
I was thinking it was
Just
something like that.
construct it to not have
in
the
terms of
elements.
minimal polynomials.
Yeah. So I mean, this idea of considering finite separable FP algebras, decomposing them, this is something you use over and over and over and over again all the time in algebraic theory. So it's good to have a sense of it. Okay.
Why does having an idempotent
We could definitely go if you have. Yeah.